All right. Today we're taking a look at work and energy in Chapter 5, starting out with a quick definition of what we mean by work. You have an intuitive experience and feeling for what work is in terms of an exertion of some sort, but in physics we have an exact definition, and that is that if we have an object that we're applying a force to, and that force results in the object accelerating over a distance x, then that means we are doing work on the object by the amount of the force times the distance parallel to that force. As you can see in the formula right here, let's see if we can animate this a little bit. Here we go. I'd take a highlighter here, perhaps. Okay. Maybe a different color would be good. Okay. So in this formula right here, the force and the distance, d, may not necessarily be parallel. That's what I'm referring to, the picture on page 82, where you see a box and the force is at an angle to the direction of the displacement d. So really all we're interested in is how much of the force is actually parallel to the direction d. So that's what this little subscript reference here on F, and with the two lines means F parallel, the amount of force parallel to the distance d. So if we were to sort of write that like this, that means F parallel is actually equal to F cosine of the angle theta, where theta is the angle between direction that you're moving and the direction of the original force. Okay? Now let's change that to a different pen so it's a little bit thinner. Okay. Now, this is just simply a mechanical definition. It says this is how we calculate work. And if you think about the units here, we have the units of the Newton for force and meter for d, distance. So that's the unit of work. It is also, it defines for us the unit of the joule. So you can express it either way. Okay, now, so work is something that an external agent does on an object, right? So just and Newton's law tells us the effect of that force is to take that object, whose mass we would know, and accelerate that object. And then that acceleration in turn will change the velocity of that object as time goes on or as distance goes on. And we can go back to our kinematics equations and then figure out where it ends up, how long it takes to get there, and how fast it's going. Okay, so we're just connecting the dots here. So the force in this expression here, you have to go back and think, okay, that force may be given to me numerically, or that force may be the result of something that we know that's applied to the object, like a spring or the gravitational force, so we can calculate it. Or perhaps we've been given some information about the velocity, distance, and time so that we can calculate the acceleration, and then therefore the force that is responsible for that acceleration could be calculated from Newton's second law. Okay? So the nice thing about work and energy is that these are no longer vector quantities. Fd cosine theta is a scalar. Okay? And so are the concepts of kinetic energy and potential energy that we used in lab last week and in this week in the online lab. The scalars are easier to deal with because we can just simply add or subtract the values that we get. We don't have to worry about Pythagorean theorem or anything like that. Yes, I know there's still the angle theta there, but that just simply is there to tell you that the only amount of work that's important for what we're doing here is the amount of work that's parallel to the direction that we're moving. Because if you think about it, if you have a vector, well, you can see this. I'll point it that way. If you have a vector force that direction, the portion of its horizontal is the one that's pulling you to the right. The portion vertical is not helping you. Okay, so that's sort of irrelevant. This is the portion we want to know, and that's F cosine theta. Now, work and energy are related through a work-energy theorem, and the following two relationships shown down here and here are two relationships that you should discuss in your lab report for the 2 weeks of lab. This first relationship was one in which you could kind of think about it in terms of what we did with shooting the ball up. Was the ball had kinetic energy at the bottom, didn't it? We shot it up and it had zero kinetic energy, and then essentially gravity did work on that ball and changed the potential energy of the ball from 0 to a maximum value. And so we kind of have a combination of these two formulas that we applied in that actual lab, where we ended up with the final energy was mgy, that's the potential energy of gravity, and the initial energy was 1/2 mv squared. But let's go back and talk about these two expressions that we've already talked about in class. First of all, we know the definition of kinetic energy is 1/2 mv squared. Okay? And whether we're talking about original or initial V0 or V final, those are just specific points. So this is a general expression for kinetic energy. And what this relationship tells you is that if an object's kinetic energy changes from K0 to some other value, then you should look for what's doing work on it, who's acting on it, okay? Because that kinetic energy doesn't just come from anywhere. It has to come as a result of someone outside of the object doing work on it. And of course we know what work is. Work is force times distance. So look for the agent responsible for that work. Okay? Now that particular formula would be one in which an object, I'll try to represent this, is being moved along a horizontal surface and applied force. Let's apply a force directly behind it. Okay, mass M, and let's have it starting with no velocity, so V0 is 0. Okay, and it gets over here, it's got some velocity, it's traveled a distance x, right? Okay, it didn't go up or down at all, so there's no change in potential energy. So the only change is the object went from having no kinetic energy, or K0 is 0, to having some kinetic energy because it has a non-zero velocity, right? So on the left-hand side here we have F times x, right? We could put that in over here. F times x, right? On the right-hand side, we know that K0 is 0 and K is exactly this formula right here, right? And so if we could connect up the fact that Fx is who's doing the work, and 1/2 mv squared is who's got the work being done on them. What's the result? Because that's the mass M is gained kinetic energy because of the velocity, and ultimately, don't you realize? You realize, of course, that because F equals ma, right? F equals ma. There we go. That the mass is accelerated, its velocity is changed, if we were actually to connect all the dots here, we'd have MAX. Okay, that's FX, right? That's FX, MAX, and 1/2 MV squared, right? Well, look, there's mass on both sides. Let's cancel the mass on both sides. Let's rearrange this formula. It says V squared is 2AX. That should look familiar, shouldn't it? What if we added a V naught squared over here? So V naught squared plus 2AX equals V squared. Hey, that's our old friend, our old kinematic formula on our list of 5. That's the 5th one, isn't it? So that formula is actually an expression of the work energy theorem for the change in kinetic energy. Finally, if we simply go up or down and don't have any velocity, it may sound weird, but if you do it slowly, you give the object such a small amount of kinetic energy that we can ignore it. So if we take an object from an original position y0 to a final position y, right, against the gravitational field that's pointing down, right, we have to do work on it, don't we? It doesn't just go up by itself. So we have to exert a force on this. We have to nice vector, huh? We have to exert a force on this, which is exactly opposite the object's weight and equal to it, so it has to be a force of mg. And we lift it up. We in reality want to make it just infinitesimally smaller, bigger than mg, so it actually moves. So we get it moving very, very slowly, and we take it through a height change of y minus y0. Okay, and that means mg y minus mg y0. Okay, and we can factor the mg. Okay, and that would leave us with y minus y0. Well, y minus y0 is simply the displacement that the object went through. Okay, so we could call that h, mgh. Well, what's that? That's just a force, isn't it? mg times the distance d. Right? So it's just saying, hey, the work that you had to do changed the potential energy of this object, and since we did it so slow, it didn't change the kinetic energy. Okay? Let's look at applying these work energy theorems to a particular problem. Now here you have a problem of a box falling from a truck moving at a certain speed, and it slides to a stop. What's the coefficient of friction between the box and the highway, and how much work was done on the box? Alright, let's start out. Let's identify things here. 100 kilograms. Okay, so m equals 100. The box is on a truck that's moving, so the box has an initial velocity of 25. I'm going to drop units here because everything is in kilogram, meters, and seconds, so everything's going to come out properly. It slides to a stop, right? Okay, so we know that means our final velocity is 0, and it does that while traversing a distance of 50 meters. Okay? Okay. We are looking for the coefficient of friction. That's our little Greek symbol mu. Okay? Now, if we were to solve this problem using the work energy theorem, this is a horizontal problem where the box is initially sliding with 25 meter per second speed and slides to a stop, so along a level surface, right? So let's think about applying work equals change in kinetic energy. Okay. Now we have to drill down into each one of these terms. First of all, I guess the easiest one is to do the right-hand side here, because the final kinetic energy is 0, right? We know that because it has 0 velocity. And the initial kinetic energy is 1/2 m times v squared, its initial velocity. Okay. So, gosh, we've got everything on that side. We've got 625 as v squared. So times 100 is 62,500. So that's going to be 31,250 on the right-hand side. Okay. So we found out how much work was done on the box by friction, or maybe I'm making an assumption there. When you think about the box, if you draw a picture of the box and the forces on the box, okay, so the box is on the surface. Pardon my lines, they're not quite perfect, are they? So the box is moving this way with a velocity v0. Friction will be acting in that direction, right? So that means we'll get an acceleration in that direction. And we have a normal force and a weight, don't we? N, normal force, weight, W. That's kind of what our picture would look like. So the only force that is acting to slow the box down is friction. So friction is what the work will be done by friction to slow the box down. We know that in the case of a level surface, the normal force is equal to the weight, right? Equal to mg. Okay, and friction is defined as mu times the normal force, right? So we can put in mg for the normal force. We've got an expression for friction, and our definition of work is the force, right? Let's write that down here. Force that we're dealing with times the distance times the cosine of the angle between the force and the displacement d, the distance that we travel. Okay, let's grab a slightly different color here. Okay, now the force we're dealing with is the friction force. Okay, so put that in over here. We know our distance. Here's our distance, so we're going to put that in over here. What do we put here? Remember, the distance d is this way, right? But the force of friction is the other direction. So that's a 180-degree angle between the force F, little f, and the distance and the displacement d. So cosine of 180 is -1. So we're going to get a -1 from this term, cosine theta, right? So put in your normal force here, put in mu times N for the friction force here, put in your D, and you've got, then you can put an expression in here for W. Okay, and the only thing that you don't know in that expression for W is going to be the coefficient of friction, so you can solve for that. Oh, that's really pretty, isn't it? Okay. All right, let's try a different one here. Okay, now this one, we have an object that is going from zero velocity to a final velocity, and slides down an inclined plane, reaches a horizontal surface. Well, okay, you know what? We already know in this case, this is a lot like the previous problem, isn't it? Because the initial information just tells us how the object got its speed of 5 meters per second, right? So it's kind of the inclined plane is irrelevant. What we know is the object slid down an inclined plane, reached the level surface here, moving with a 5 meter per second speed. Okay? So in terms of our problem, that's our initial velocity. Okay? Slides for 2 meters, fine. Goes from here to there. Okay? So we're going to say 2 meters. So we've got our x, or our d. And it has a kinetic coefficient of friction of 0.3. So that means that on this level surface there's a frictional force F acting against the box's forward motion to decelerate it. Okay, and what we want to know is how fast is it going at the end of 2 meters. So I would imagine, again, we could use our work equals the change in kinetic energy formula. Okay. Oops. Uh-oh, I need an eraser. There's my eraser. I don't need that K0, do I? Okay, K minus K0. Okay. All right. Now, just like the last problem, the work will be the force times the distance times the cosine of the angle. Okay, no problem there. The final kinetic energy will be 1/2 mv squared. So there's the thing we're looking for, the v right there. And the initial kinetic energy will be 1/2 mv0 squared. Okay, mv0 squared. Okay. Okay. Now you're probably yelling at the screen at this point, going, "Wait, where's the mass? We don't have a mass in this problem. It just says a crate slides down an inclined plane." Don't worry. Don't worry. Just follow through on the derivation. When you put in all the information about W here, you know, friction force times distance times cosine theta, and friction force is mu times normal force, and normal force is mg. I think you'll see what happens. Okay? All right. Now let's do another. Now, one of the things that I talked about in lab was the conservation of energy principle. And the conservation of energy principle said that your total mechanical energy that you start with and you end with are the same. And to be precise, that expression is only correctly valid when there is no non-conservative force acting on the object we're looking at. Now, that's a fancy way of saying, in our case, if there's no friction, right? So think about it. If an object has a certain amount of kinetic energy at one point and it's moving along a frictionless surface, up or down a hill, whatever, there's no mechanism available to eat up energy, because that's what friction does. It converts mechanical energy into heat. Now, if we throw friction in there, then whatever beginning energy we had, in this case, we'll call it E0, okay, let's put that over here. E0, if it were 100 joules, as it slides along and goes to wherever the final point is, if there's friction in between, will it get to the end of that path with the same energy it started with? And you know the answer is no, it can't, because some of that energy had to go to overcoming friction, doing work against friction, which generates heat, which is lost energy. It's not mechanical energy anymore. It's of no use to us. So the actual final work energy theorem is kind of like this. It says the energy you start with minus the work done against a non-conservative force will equal the energy you end with. Actually, I'm going to make that positive here, okay? And the reason I'm going to make that positive is a non-conservative force is going to be a negative. WNC is going to be a negative number anyway, so it's going to be positive energy, okay? Take away the energy you'd lose due to this non-conservative force, you'll end up with positive final energy. Most of the time we rearrange that formula and it looks like this. It says non-conservative work equals the change in mechanical energy. Okay. Now, remember what the definition of mechanical energy was. E was K plus U. K plus U. Okay. So that means E final is K final plus U final, and E original is K original plus U original. Okay, so let's bring this over here. Non-conservative work. Okay. Think of that as the energy you're losing. Okay, it's being converted into heat. So E final is K final minus U. Oh, sorry, plus U final. Ha. All right, minus. Okay, now E0 is K0 plus U0. K0 plus U0. All right, now let's kind of rearrange this a little bit. Okay, K minus K0. K final minus K0. K final minus K0 plus, let's see, U final right here minus U0. Oh, you know what this is? This is the work energy theorem that we had on the first slide. Individually, work was a change in kinetic energy, and individually, work was a change in potential energy. And now we see that work is actually the change in each one of these. Okay, so this is really a general work energy theorem relationship. It's kind of like an accounting principle. That is, you start out with a certain amount of K and U. Okay, you subtract the work, non-conservative, and you end up with the final K and U. Okay, so let's try to apply this to the problem at hand. We have a car that has an initial velocity, V0, and we have a height, let's call that Y, at a 20-degree angle, and a coefficient of friction. Okay? I'm going to make a quick conversion here. What is 45 miles an hour is 20.12. 20 and 1/8, 0.125. 125 meters per second. Right, okay. Now, the thing about non-conservative work is the only one we have to be concerned with in our problems is the friction is going to be the force that is responsible for non-conservative work in our problems. Okay? And so, in our case, the non-conservative work will be the friction force times the distance times the cosine of the angle between the distance you travel and the friction force. Well, all right. So, see if we can squeeze this in down here. Let me grab a different color here. Okay. Car is approaching a hill. Okay. Here's our hill. It goes up, 20-degree hill. And let's just level it off. I don't really care if it's level at the top or not. Okay. And we'll put our car down here. Okay. Moving with an initial velocity. V0. Okay. Now, when the car is on the incline, so, well, really the question is, notice what the question is, can the car coast from the bottom of the hill and make it to the top? So that means at the top, the critical condition would be, can I reach the top and have zero velocity? Okay. Do I have enough energy at the bottom to reach the top with zero energy? That would be easy if there were no friction. We would just equate the kinetic energy at the bottom, K0, to the final potential energy at the top, and we wouldn't have any non-conservative work with no friction. But we have friction, right? And friction says the coefficient of friction times the normal force times the distance times the cosine of the angle between the friction force and the distance. Okay. Okay. Now there's a possibility you could get a little confused on this problem because of all the different angles, right? This angle theta right here, this one right here, the cosine of theta, that is the angle between the direction of the friction force. So remember, the object is moving up the incline, so that's the direction of its motion. So friction is acting down the incline, isn't it? Okay, a little f right there. But it's the x value is going up the incline. So the cosine theta term there is between the angle between f and x, isn't it? Well, that's still 180 degrees, so that still means the cosine of theta is -1. So don't be confused. That's not this theta up here in the problem. It's not the 20 degrees. Okay. All right. All right. So now, but where does this 20 degrees come in? Well, how do we find the normal force? Well, the normal force, remember, is the perpendicular vector. Oh, I drew that really bad, didn't I? It's perpendicular to the surface, right? And the weight is acting straight down. The normal force is perpendicular, and we've done this before. The normal force for an object on an inclined plane is mg cosine theta, right? And that theta, that's the 20 degrees. Okay. Okay. So you kind of get in the flow of this here. Here's your non-conservative work expression. Well, that's fx cosine theta, where n is mg cosine theta, or 20 degrees. It's this cosine theta is -1. X is the length along the incline. Let's see, we know this angle, we know this height, right? We know that height y and this angle 20 degrees. So we can find x. We know x. Whew. So we've got, if we end up at the top, the question really is this. Let's see. Let me go back to a little more highlighter here. Let's change our color back to red. Okay. If we start at the bottom, U0 is 0. Why? Because that's our reference level, ground. Okay. And if we want to just get to the top, that would mean the final kinetic energy would be 0. Right? Okay. K0, we know 1/2 mv squared. U final would be mgy. Right? So those two terms on the right hand side. On the left hand side, we have the non-conservative work. Mu n mg cosine 20 x. Okay, and don't forget that this cosine is -1. Okay, not the same cosines, are they? So what we're trying to find out in the end is does this side, is it greater than or less than what's on this side? Okay. If the left-hand side is bigger than the right-hand side, then we don't have enough energy to get to the top. Okay, so if it's not, then we do have enough energy. Oh, that's really colorful, isn't it? Okay. Now, well, here's one. Here's another one of your homework problems. We have a 2 kilogram. I'm missing a word there, huh? So I guess we'll put the word child in here, right? 2 kilogram child swings on a playground swing. If the swing hangs down 2 meters from the top bar, okay, so here's our swing and here's our child. Okay, M and L. Okay, so we've got M and L. Child swings out 20 degrees, so let's swing this out here, 20 degrees. Okay. What is the height above the ground at this angle? I don't know what the original height is. I didn't specify it, did I? So if we just say this is h, and we really want to know what is this height, h plus something else, right? And what is the change in potential energy? Okay. Oh, let's take a let's use the symbol of an h primed for the total height as the child swings out. So h primed will be that total distance. Oh, it's not too good, is it? All right. Total distance, original height h. Okay. So in terms of potential, gravitational potential energy, originally the child's potential energy is mg, h, and the final potential energy is mgh primed. All right. Okay. Now, this looks kind of like a triangle, doesn't it? What if we just simply draw a line back, perpendicular line back, and create a triangle out of that, right? This length of the hypotenuse is still L. That's the original length. This is swung up, so that's still L. So this 20 degrees. So notice that this purple L here is the original length, but the side, the cosine side of the triangle is less than L, isn't it? So if this is 2 meters here, then this portion right here we could calculate by using the cosine of 20 is equal to the adjacent side over the hypotenuse, 2. Let's just plug that in. 20 cosine times 2. 1.88. Okay, so that means the adjacent side is 1.88 meters. Now the original length was 2 meters, so now that's the original purple line. The red line is 1.88, so the difference between the height here to here, or common center to center, whatever, is going to be 2, right? 2 minus 1.88 equals 0.12 meters. That's how much higher from the original h that the child rose up, right? So h primed is going to be the original height plus 12 centimeters, 0.12 meters. Therefore, h primed minus h, the difference is 0.12, right? So when you come up here and take that and do what is the change in potential energy, delta U is U final minus U original is mg h primed minus h. Okay, I think you can handle the rest of that. Alright, so I wanted to see a few of these problems from the homework for today. And let's see, we need to have a problem that you can hand in here. So let's, I wonder if we can see what... Alright, here is your problem for your points for today for this virtual lecture. Okay? We have 3 forces that are acting. 10 newtons, 8 newtons, and 12 newtons. And the vectors are shown here on the diagram. And we want to know how much work is done by the force at 0 degrees. In other words, how much work is done by F1 in this situation. So you should send me the answer to that question. Okay? Actually, what I'll do is I'll put an assignment in Chapter 5. It'll be the virtual lecture extra credit points. And you'll submit your answer to that assignment tab. Okay? So find the work done. Find the work done. All right.